Voltage across a load is given as 100 sin omega t, and current through the same load is 100 sin omega t minus 60 degree, 10 sin omega t minus 60 plus 2 sin 3 omega t. This is third harmonic and this is fifth harmonic. We will not say it as harmonic. We will just say here the frequency of current is same as the frequency of voltage, and in these two cases the frequency of the current is integral multiple of frequency of this voltage source. Then we have to find out power consumed by the load in watt. Average power consumed by the load. In network we have studied that whatever formula for power we know, the formula of power is Vrms Irms cos phi. This is nothing but this is average power. We always talk about average power, so there is nothing new in the question if they ask about average power. We just have to find out the value of power through the load. And in the derivation of this formula we studied that power in a load is consumed by, or you will get non-zero value of power due to same frequency of voltage and current. It means this voltage will give you non-zero value of power with this current only, because these two quantity have same frequency. With the interaction of this voltage and this current you will get zero power because the frequency are different. Okay, so the average power will be Vrms, which is 100 by root 2. This formula is also, this can also be written as Vm by 2 into cos phi. So V maximum is 100 volt, I maximum is 10 ampere divided by 2, and the phase difference is 60 degree, cos 60. This will give you 250 watt. If you will find out with the help of average, we will first find out instantaneous power. Okay, the instantaneous power will be 100 sin omega t into, instantaneous power is nothing but Vt into It. Okay, so this will be Vt is 100 sin omega t and It is 10 sin omega t minus 60 plus 2 sin 3 omega t plus 5 sin 5 omega t. Now average power will be, or Pt will be 100 sin omega t, this is 1000 sin omega t sin omega t minus 60 degree plus 20 sin omega t into sin 3 omega t plus, not 20, you will have 200 plus 500 sin 5 omega t, 500 sin omega t into sin 5 omega t. This is the value of instantaneous power. Now to take average power, the average power will be 1 by t integration over t pt dt. Okay, so we need to integrate this dt from 0 to t, where t will be 2 pi by omega. Integrated dt, and if it is periodic with t, this will also be periodic with, its time period will be, if this function is periodic with t, this will also be periodic with t, and integrate it also 0 to t. Now when you will calculate for, when you will solve for this integration, you will get here 0, here also 0, and after solving this you will get 250 watt. Here you will get 250 watt. If sine omega t is periodic with t, while finding out this integration, you will use formula of sine a into sine b. Then you will get sine a plus b, or cos a plus b. You will get cos a plus b, omega t plus 3 omega t, 4 omega t, minus cos, or cos 2 omega t minus cos 4 omega t, and some constant also. So if sine omega t is periodic with capital T, here you have 2 omega t, so this will be periodic with t by 2, this will be periodic with t by 4, and we are integrating it from 0 to t. So even if you integrate it from 0 to some integral multiple of time period, what we are doing, we are integrating for from 0 to t, that is 2 into t by 2, here 4 into t by 2, there will be no effect on average value. If you are integrating for a duration which is integral multiple of time period, there will be no effect on the average value, because to find out average you will divide it by same duration. Here also you will have 1 by t. A 3-phase diode bridge rectifier is feeding a constant DC current of 100 ampere. The load current from the three-phase diode bridge rectifier is constant at 100 ampere, okay, to a highly inductive load. If the load is highly inductive, current will be continuous and constant. If 3-phase 415 volt 50 Hz AC source is supplying to this bridge rectifier, then the RMS value of current in each diode is in amperes. We have to find out RMS current through each diode. Okay. In diode bridge rectifier, the load is taking constant current of 100 ampere. This is 3-phase supply. So current is continuous here for 360 degree, and if current is flowing, one diode from the positive leg and one diode from the negative leg must conduct, because if current is flowing here, current will flow in this direction, so this current must be supported by either of these three thyristor or diodes. So one of these three diode will conduct, and similarly if current is coming here, so one of these three, this current will pass through either of these three diodes. So at one time 2 diodes will be conducting. At a time 2 diodes must conduct. Okay, so current has to flow for 360 degree, and from the positive leg, in the positive leg, out of these 3 diodes, one diode has to conduct. Okay, and condition for each diode is symmetrical, so each diode will conduct for 360 divided by 3, that is 120 degree. Okay. Similarly, here also condition is symmetrical. So each diode will conduct for equal duration. Total duration is 360 degree divided by 3. It means each diode conducts for 120 degree in case of continuous conduction. And also current through diode must be equal to the load current. Okay. So out of 360 degree, let's say this is a span of 360 degree, any diode will be conducting for a span of 120 degree only. And the magnitude of current through a diode will be equal to load current, that is 100 ampere. So the average current through diode will be this area 100 into 120 degree divided by total span is 360 degree. Let's say this is I naught. So average current through diode will be I naught by 3, and RMS current will be, first take a square of value I naught square into I naught square d theta from 0 to 360 degree divided by 360 degree. But in the span of 0 to 360 degree, this value is I naught has non-zero value only for 120 degree. This will be 1 by 360 into I naught square into 120. This will be I naught square divided by 3. What is this? This is mean square value, and if you will take root of this quantity, you will get root mean square. So IRMS through diode, this will be I naught divided by root 3. I naught is 100 ampere divided by root 3. So this will be answer. This is a circuit diagram of DC-DC buck boost converter. Okay, this is the solid state switch. Here we have a solid state controlled switch, then inductor, and here we have load. Okay, when the switch is connected or when the switch is turned on, current will rise through the inductor in downward direction. Okay, and when the switch is turned off, the build-up current through the inductor, this will find path through load and this diode. It will circulate in this direction. Okay, so the actual polarity across the load will be this. Okay, and since a large capacitor of 1000 microfarad is a large value of capacitance, a large capacitor is connected here, so this capacitor will make this output voltage constant. This is 36 volt. So we have to find out the peak voltage across the switch. So when the switch is conducting, the voltage across the switch will be 0 because it is conducting, and the switch is ideal, there will be no voltage drop. Okay, current flows in this direction through the switch. So let's say this is the reference of switch voltage. This is reference of switch voltage Vs. Now when this switch is turned off, the inductor current will flow through this path. Okay, if it flows through this path, this diode will be short circuited. This diode will be short circuited, and this is reference for switch voltage. Source voltage is 24 volt. Now let us apply KVL in this loop. Okay, here you will have gain of 24 volt, here drop of switch voltage, and here this is actual polarity. So if you will move in clockwise direction, here you will have a gain of 36 volt plus 36 volt, and loop is completed. This is 0. So Vs will be plus 60 volt. So the forward voltage, the forward blocking voltage across the switch will be 60 volt. This is a question of full bridge converter. Here resistance is 20 ohm, the DC voltage is 800 volt, AC voltage source is 200 pi sine 100 pi t, and firing angle delay is 120 degree, and inductor current is inductance is large enough to make the output current as a constant DC current. Okay, and in full bridge converter and also in three-phase full bridge converter, this is single phase, we have studied that if alpha is greater than 90 degree, this converter is operated as inverter circuit. It means in converter circuit, what we expect, if it is a converter circuit, we expect that power will flow, real power will flow from AC to DC. Okay. Or real power will be observed in this DC voltage source. Okay. Here polarity will be reversed, otherwise current will not be continuous. Okay, but if the polarity of voltage source, constant voltage source or DC voltage source is reversed and alpha is made greater than 90 degree, this converter is operated as inverter. In this full bridge converter operates as if it is an inverter. It means real power will flow from DC side to AC side. P will flow from DC to AC. It means, let's say this is the direction of current. This is only the possible direction of current, because if current is flowing in upward direction, neither of these two thyristors will support that current. Okay, so if current is flowing in downward direction, obviously this battery will deliver power because current is coming out from the positive terminal of this voltage source. Okay, so now we have to find out the real power fed back to the AC source. Here we have AC source. Okay, we have to find out how much power is fed back to the AC source, real power. So let us first find out the average voltage of this converter circuit, because we have formula for that. The average voltage V0 is 2 Vm divided by pi cos alpha. 2 Vm is 200 pi divided by pi cos 120 degree. This will give you 400 into minus 1 by 2 minus 200 volt. Okay, it means instead of this AC source and this bridge converter, we can connect a DC source of minus 200 volt. If it was plus 200 volt, we would take positive here and negative here, but it is minus 200 volt, so the positive will be here and this will be negative. This is 200 volt. This is equivalent, or this is average voltage of this AC source or this converter circuit. Now we will connect the remaining part of the circuit. This is 800 volt, this is 200 volt. Okay, then what will be the value of current I? These are DC voltage sources, or in full bridge converter we have studied that if current is continuous, or even if the current is continuous and if it is periodic, the average voltage across the inductor will be 0. Okay, we can say that if IL is periodic, this is very useful concept. If inductor current is periodic, then average voltage across the inductor will be 0. This is called flux balance, and I have used flux balance throughout the phase control rectifier and chopper circuits. Okay, so we can say that this V naught, if we apply KVL here, let us move in clockwise direction. So here we will have drop of 200 volt. Let's say this is VL, this is VR, and this is 800. So while moving in clockwise direction, here we will have a drop of 200 volt, here minus VL, minus VR, and here gain plus 800 volt equal to 0. Now if you will take average, okay, so these are constant. Average of minus 200 will be 200. And what is average of VL? Since inductor current is periodic, okay, it is given that inductor current is a DC current. So for DC current, inductor voltage will be 0. Even if this current is not DC, what I am trying to say, if current is complete DC, current is constant here, then inductor voltage will be 0. But even if the current is not constant, current is varying little bit, but if inductor current is periodic, the average voltage across inductor will be 0. So this voltage is 0. Average voltage across resistance will be the average output current into resistance plus 800 equal to 0. So I naught will be 600 divided by resistance is 20. This will be 30 ampere. Okay, so 30 ampere current is flowing here. So power absorbed by this source is its voltage, and since current is entering into the positive terminal of this source, so this source will absorb power, and magnitude of that power will be 200 into 30. This will be 6 kilowatt. And what is this source? I have connected this source of average voltage instead of this AC source and switches, and this combination takes 6 kilowatt, and but switches are lossless. So where this 6 kilowatt power will go? This 6 kilowatt power will be absorbed by this AC source. So this will be our answer. The real power fed back to the AC source in kilowatt is 6. This circuit diagram is of 180-degree conduction mode, 3-phase voltage source inverter, and here we will have the 3-phase output voltage. The voltage between the two line will be, this is line to line voltage. Okay, in case of 180-degree conduction mode, the value of line to line voltage, the RMS value of line to line voltage is root under 2 by 3 into Vs, where Vs is the voltage of this DC source. Now loads are connected in delta, so each resistance will get a voltage of line to line. So power consumed in each resistance will be VLL square divided by R, and there are 3 such resistances, so the total power consumed will be 3 into VLL square divided by R, and this is the power we are required to find out. So this will be 3 into square of this 2 by 3 into Vs square divided by R, 2 into 600 into 600 divided by 20. This will be 36 kilowatt. The resistance is 30 ohm, not 20 ohm. if we will use 30 ohm, we will get 36 divided by 3 into 2. 24 kilowatt will be the correct answer. The power consumed by this delta connected 3-phase load will be 24 kilowatt. This is solid state switch. Instead of this switch, in the theory lecture I have shown just a switch S. The input voltage is 360 volt, output voltage is 400 volt, and the power is 4 kilowatt, 4000 watt. So the output current I naught will be 4000 watt divided by 400. This will be 10 ampere. The output current will be 10 ampere. The devices are ideal considering continuous inductor current. The RMS current in the solid state switch is, we have to find out RMS current through this switch is. Let's say this is current IS, so we have to find out RMS value of IS. So to find out this value, let us first find out the graph of the switch current IS. Or before drawing the switch current, let us first draw the inductor current. In the theory lecture, by drawing inductor current only, we derived the result V naught equal to Vs divided by 1 minus D. Okay. So let us first draw the inductor current. Let's say this line represents the average value of inductor current. When this switch will be connected, the inductor current will grow according to 360 volt. Okay, this inductor current will grow. Okay, so let's say at this point the switch is connected. So from this point inductor current will start growing. So the point where inductor current will start growing, this will be the minimum value of inductor current. Let's say this is minimum value of inductor current, and this is maximum value of inductor current. Okay, so if it starts growing, it will start from minimum value, and the point where it stops growing will be the maximum value of inductor current, and the duration for which this switch will be connected will be T on. Similarly, when this switch is disconnected, the established value of inductor current, this will take path of load. Now in this case, or when the inductor current was growing, what was the slope? The voltage across inductor was, this is 360 volt. So if we will move in this loop, this switch is connected, so it will provide a short path. So if you will move in this loop, VL will be 360 volt. So the rate of increase of inductor current will be according to 360 divided by L. For detail, you may refer the theory lecture of chopper circuit. Okay. Now when this switch is disconnected, this established inductor current takes a path of load. Now if you will move in this loop, here you will have a gain of 360 volt minus VL, here a drop of 400 volt equal to 0. So VL will be minus 40 volt. So voltage across inductor is negative, so this current will now decrease, and the duration for which switch will be disconnected, this will be called T off. Okay, so Now if you are interested to draw the graph of switch current IS, the current will flow through the switch only when the switch is connected, and switch is connected for the duration of T on. And when the switch is connected, inductor current takes the path of switch only. So during the duration of T on, switch current is nothing but inductor current. So if you are interested to draw inductor current, you will draw the graph which is same as inductor current during the duration of T on. This is average value of inductor current, and this is switch current. And after this point, switch current will be 0. This is the graph of switch current. Okay, so to find out the RMS switch current, we need to first find out the equation of this line from 0 to T on. Okay, to find out the equation of this line, we need the minimum and maximum or average value of inductor current. The RMS value of switch current, the expression for RMS value of switch current will be the instantaneous switch current square dt from 0 to T 1 by T to power half. Okay, because this current will be periodic. Up to this point it will be 0, and after this point again it will take this same shape. This is the shape of switch current. So to find out equation of switch current, let us first find out the average inductor current. Let me first draw the circuit diagram of boost converter. Here you have inductor, here you have main switch, and this is load. Okay, so the output power, this is V0 into I0, and input power will be the input voltage, source voltage into the average source current. And if you compare the source current and inductor current is always equal to the source current. In the circuit diagram, this is very obvious that the source current is always equal to inductor current. Now all the switches are ideal. In the question it is given all the devices are ideal, so there will be no power loss. If there is no power loss, input power is equal to output power, so Vs into Is average is equal to V0 into I0. So Is average, which will also be equal to inductor current average, will be V0 I0 divided by Vs. Okay, V0 is 400 volt, I0 is 10 ampere divided by Vs is 360. So this will be 100 divided by 9 ampere. So the average inductor current is, this is 100 divided by 9 ampere. And what will be this ripple? What will be this height? This height will be this slope into this width. This width is T on by time, T on by 2. Okay, so to find out RMS value of switch current, we need to find out equation of this line. And to find out equation of this line, along with the slope, we have the average value, but this is not sufficient to find out the equation of this line. We have slope 360 divided by L. Slope is given, this inductance is given as 10 millihenry. Slope of the line can be calculated. This is 360 divided by L is given. So this is slope this point is 100 divided by 9. Okay, so equation can be found out. Let's say you have found out the equation is. Now you will integrate equation of is from 0 to capital T, and in 0 to capital T it gives non-zero value for t on duration only. So what you will do, you will integrate it from 0 to t on, but in the question t on is not given. Okay, the switching frequency is not given, so you cannot calculate the total time. Obviously input voltage and output voltages are given, so you can calculate the duty cycle. The output voltage 400 volt is equal to 360 divided by 1 minus d. Okay, so from here you can calculate d as 1 by 10. So if d is given, t on is equal to d into t. The duty cycle is given, but the total time is not given, so you cannot calculate t on. If you cannot calculate t on, so this expression cannot be calculated. Okay, but still we have to find out the RMS value of switch current. So there is, if we assume some approximation, we can approximately find out the RMS value of switch current. What approximation I am going to use? Since the inductance is very large, so the variation in this inductor current will be very less. Let's say this variation is not very large. Okay, let's say this is inductor current. This variation is not very large. Okay. Then how will be the graph of switch current? This will be the graph of switch current, and in this duration we can assume that this switch current is constant. Roughly we can assume that switch current is constant. Here also the inductor current is approximately constant. Now if it is constant, that constant value will be average value. So here also the constant value of switch current will be 100 by 9 ampere, and this will be for a duration of 0 to t on. So now we have graph of switch current as 100 by 9 ampere for a duration of t on, and this will be periodic with time period t, where t is the total switching interval. Okay, now we have to find out RMS current. So RMS will be, RMS of this kind of graph is, let's say this height is I naught. So RMS of this kind of graph is I naught into root under, in the numerator will be the duration for which this value is constant, divided by, in the denominator you will have the total interval t. This will be the RMS value of switch current. And for calculating average switch current, I naught into simply t on by t. You need not to take root. Okay, so I naught will be 100. I naught is 100 divided by 9 into root under. T on by t is nothing but duty cycle. So 100 by 9 into root under 1 by 10. This will be 3.51 ampere. This is a circuit diagram for this circuit diagram is for bidirectional voltage source converter, where this is 220 volt AC voltage source which is connected to this converter circuit through a 5 millihenry inductor, and here we have a 400 volt battery which is to be charged with power of 5 kilowatt. 5 kilowatt power. With this much power, this battery has to be charged. This phasor diagram is also given in question. This is Vs, AC source voltage. Is is this current, and in the question phasor of Vs and Is is in same direction. It means this source is providing power at unity power factor. Okay. And Vc1 is this voltage. This is not given in the question, but I hope this voltage is Vc1. Between main voltage and the fundamental AC RMS voltage source converter voltage Vc1. It talks about fundamental AC RMS voltage source converter voltage. It talks about fundamental component of voltage source converter voltage. Now, if these switches are operated, what will happen? How will be the actual shape of Vc1? If you want to draw the graph, when these two switches are operated, let's say this is the reference for Vc1. When this switch is connected, the positive reference will be connected to the positive terminal of this battery, and this negative through this switch will be connected to negative. So Vc1 will be positive 400 volt. When these two switches will be operated, through this switch, the negative reference of Vc1 through this switch, this will be connected to positive of the battery voltage. So in this case, when opposite pair of switches will be operated, the voltage will be minus 400. So this type of waveform we will get at this point. Okay. So this is a square wave. So there will be a fundamental component of this voltage, because after this point this is a constant voltage 400. So there cannot be any fundamental component of this DC voltage, constant DC voltage. So this voltage is Vc1, and we have to find out, this is not actually Vc1, this is voltage, let's say this is voltage Vc or V, and fundamental component of this voltage will be Vc1. If you will take Fourier series, there will be some fundamental component. So we have to find out the angle delta between source voltage and fundamental component of this voltage, that is named as Vc1. Okay. So now let us say the fundamental component of voltage is Vc1 here. Okay. So instead of, and this Vc1 will be because of this 400 volt DC source. Okay. So instead of this much circuit diagram, I am just connecting a fundamental voltage source of Vc1 here. So what will happen? We have a 220 volt AC source, an inductor, and here we have a Vc1. Okay. This is 220 volt. Okay. Now this battery takes 5 kilowatt. Okay. So 5 kilowatt will flow from this AC source, Now instead of this 400 volt and all these switches, I have just connected one AC voltage source. So obviously 5 kilowatt power will go into this voltage source. Because switches are ideal, so switches will not take any power. And in the phasor diagram, the source current Is is shown with the source voltage. So the power given by the real power given by this source is Vs Is cos phi, and cos phi is 1, and total power given is 5 kilowatt. So 5000 watt is equal to 220 volt into Is. So the source current will be 250 divided by 11. This will be 22.73 ampere. And what will be the reactance offered by this 5 millihenry inductor? The reactance XL will be now what I am going to do, let's say this voltage is Vs, this voltage is Vc1. So if you will apply KVL, Vs will be equal to Vc1 plus voltage drop across inductor, and voltage drop across inductor will be Is into X, JIs into X. So Vc1 will be Vs minus J Is X. So now if you will draw the phasor diagram, this is Vs and this is the direction of Is. So what will be the direction of JIs? If this is direction of Is, JIs will be anti-clockwise 90 degree. This is the direction of JIs. Then what will be the direction of minus JIs? Minus JIs will be in the downward direction. So Vs, this can be written as Vs plus minus JIs into X, and minus JIs is in downward direction. So Vs, this is direction of minus JIs X. So this vector plus this vector is Vc1. This is Vc1. So this is the phasor diagram given in the question. And this is delta. So what will be the value of tan delta? Tan delta is nothing but this height divided by this length is Vs. And what is this height? This height is magnitude of this vector. This will be Is X divided by Vs. Okay, Is we have calculated as 22.73 divided by Vs is 220, and X will be reactance of the inductor. This will be omega into L. And what is omega? For 50 Hertz, this is source frequency is 50 Hertz. So omega will be 314 radian. Okay, omega will be 2 pi into 50. 100 pi means 314 radian into 5 millihenry means 5 into 10 to power minus 3. So this will give you tan delta as 22.73 into 1.57 divided by 220. This is 0.1622. So delta will be tan inverse of this. Tan inverse of answer. This will be 9.21 degree. Okay, so in this question there was nothing about power electronics. No concept of power electronics was used. but from the circuit diagram it looked like this question is from power electronics.